Okay, the trick to this assignment is to keep in mind that momentum is a vector because momentum equals mass. Equals mass times velocity, and since velocity is a vector, that makes momentum a vector. And the idea is whatever the momentum is of the system is to begin with is what it ends with. So the way Newton expressed his idea of his third law is, look, however much momentum a force generates in one direction is also what it generates in the other direction. So if you take the mass of one object times the velocity of that object, it's going to equal the mass of the other object times its velocity, provided they both start at rest. So let's just try this for the first one. So I have a cannon that's going to shoot a cannonball. So what we've got is this. Let's see, the cannon has a mass, so we'll make the cannon M1. So the mass is 1785 kilograms. That's the mass of the cannon. I'll put the kg so you remember. Times the velocity of the cannon, which I see here is 2 meters per second. Now that's going to equal the mass times velocity of the cannonball. So the cannonball I see has a mass of 12 kilograms times a velocity that I don't know. So I'll say times v2. So clearly what I do is divide both sides by 12 kilograms. Kilograms will cancel out, and what I'll end up with is V2 equals 297.5 meters per second. Now if I want to be good about significant figures, I gotta say, you know what, I only got one significant figure here, I should round this to one significant figure, and if I do, what I get is 300 meters per second. You didn't think we were going to forget about significant figures this late in the year, did you? Let's try number 2. Okay, again, I'm going to make the catapult object 1. And I'm going to make the boulder that throws M2. So what I've got here is this. I don't know what M1 is. That's what I'm trying to find. What is the mass of the catapult? I'm making that M1. So I'm going to say M1, that's a 1, times the velocity of the catapult, which is right here, it's 3 meters per second, times 3 meters per second, equals the mass of the boulder, which is 314 kilograms. And by the way, it's really useful to learn that kilograms measures mass. That would really help you guys. Times the velocity of it, which is 45 meters per second. So to solve this, then what I do is I have to take both sides and divide them by 3 meters per second. Meters per second will cancel out, leaving me with kilograms, which is what I want. So what I find is that M1 equals 4710 kilograms. And again, if I'm going to round that for significant figures, since I stupidly gave us a single significant figure to work with here, I should probably round that to 5,000 kilograms. Man, I wish I'd figured this out. Okay, let's keep moving on. We're doing great. All right. Ooh, I love this one. Okay, so what I've got is a person who has this mass is on a boat with this mass. So I have M1, M2. Now the person runs here, so I now know M1 and V1. So let's just go ahead and do that. M1 is going to be 65 kilograms, and V1 is going to be 5.2 meters per second. Now that's going to equal M2, which is the boat, which is 894 kilograms times the velocity of the boat. Now what I have to do is divide both sides by 894 kilograms. And what that's going to give me is the velocity of the boat is 0.378 meters per second. It doesn't go very fast, does it? Well, that's not surprising since it has such a large mass compared to the person running on it. But I'm not done yet, because what I was asked to find here is how far the boat moves. And therefore that's a distance. So I'm going to use the equation that says that velocity equals distance over time. And I'm solving that for distance, so the velocity is right here. There's my velocity, so I'm going to say 0.378 equals the distance divided by the time, which I was told right here is 3 seconds. So I had to multiply both sides by 3, and when I do, what I come up with is the distance the boat moves is 1.134 meters. And looking at all these values here, I got two significant figures, 2, 3, 2. I got around to two significant figures, so therefore I'm going to say the distance equals 1.1 meters. Let's keep going here. Ooh, the rabid pygmy rhino. Oh, that's a scary thing. Alright, let's see. The question is, how fast would you need to throw a rock in order to stop it in its tracks? So in other words, the momentum afterwards has to equal 0. So instead of these two things starting at 0, in this case they're going to end at 0. So I need to take the mass of the rhino, make that M1, which is 58 kilograms, times its velocity, which is 6 meters per second, is going to equal the mass of the rock, which is 5 kilograms, which is a pretty hefty rock, times its velocity. So when I solve this for V2, which I think you know how to do now, because nicely these all solve the same way. I think that's pretty great. You just always have to divide by something. Let's see, what do I get then? Hang on a second. The velocity I then get is 69.6. That's a pretty fast rock. Well, that's how fast I had to throw it then. I had to throw it at 69.6 meters per second, which is pretty darn fast, I must say. That's like 130 some miles an hour. But you know what? You're desperate. You could do this. Alright, now I have a 65 kilogram person jumping on an airplane, pulled towards the earth with a force of this many newtons. If the earth has as much, okay, let's see, how fast does it accelerate upwards? So in this case, I'm looking for acceleration, right? And what I know is, here's the mass of the earth, here's the force the person's acting on it. I don't think I even have to know what the mass of the person does in this case, because I think I can solve this just using Newton's second law, in this sense, that what you have to remember is, however hard, let me draw a person, and this is an idea that's hard for some kids. Here's a person, here's the earth. Remember, it's not just that the earth pulls down on the person. Newton's third law says the person is pulled down on the earth with the same amount of force that the person pulls up on the earth. They both pull on each other. A force isn't a one-way thing. It acts between two objects, in this case the person and the earth. So therefore, if the force of the earth pulling down on the person is this much, 637, that's also how hard the person pulls up. So we want to find out is how fast does the world accelerate towards this dude. So here you go. I'm just going to use this simple relationship. Acceleration equals force divided by mass. Newton's second law. So let's see. For acceleration, that's what I'm looking for. So I'm just going to say acceleration equals the force is 637 newtons. And the mass is 5.97 times 10 to the 24th kilograms. And when I solve that, what I'm going to find is that it doesn't accelerate very fast. It accelerates at about 1.07 times 10 to the negative 22nd meters per second, which is about like, half the diameter of a proton per second. And yet it moves, to quote my man Galileo. Alright, let's keep going here. Alright, the Earth has this mass and this much orbital velocity. Venus has this mass and this much orbital velocity. I got these values straight off the internet, so you know they're right. So the question then is, which planet has more momentum? Well, that just means I had to multiply mass times velocity. So let's start with Earth. The mass times velocity of the Earth. Mass times velocity. Let's see what I've got here. For the Earth, its mass is 5.97 times 10 to the 24th times its velocity, which is 2,9,800. And that's going to give me a momentum of 1.78 times 10 to the 29th. Unfortunately, we really don't have any unit like newtons. Instead, it's sadly just kilogram meters per second. I hate that. Well, anyway, let's try what it is for Venus. For Venus, I'm going to take the mass times velocity. It's going to be 4.87 times 10 to the 24th kilograms times its orbital velocity, which is faster since it's closer to the sun, 35,000 meters per second. And what we find is that Venus has a momentum of 1.70 times 10 to the 29th. So, oh, look at that. That's kilograms meters per second. Turns out that the Earth has more momentum. Welcome to the back side of your homework. Why can't an astronaut swim back to her spaceship? Well, there's different ways you could answer this. One way you could say is there's no outside force. You could say that if she pushes on nothing, nothing pushes on her. I don't want to write these. You could say that there's no momentum that can be generated because there's no mass being pushed the other way. You could say a force must exist between two objects, and she's a single object. There's lots of different ways. I like to say, if you push on nothing, nothing pushes on you. All right, but there's different ways of stating how Newton's third law could be used to explain this. I'm just too lazy to write them all down with this stupid stylus of mine. All right, let's try this next one. What I've got is I have this much exhaust is pushed out of a rocket engine, and each particle comes out with this velocity relative to the rocket. How much does the momentum of the rocket increase? Well, let's just see here. If I have 2,400 kilograms of material, and it is going to come out at 250 meters per second, then that is a momentum change of 600,000, that's a comma by the way, kilogram meters per second. And so since I'm generating that much momentum in a downward direction with the rocket exhaust, I have to generate that much momentum upwards for the rocket. A 25 kilogram shopping cart is traveling. Ooh, I like this one here. Okay, so let's just try this one. This one takes a little bit of thinking. So I got a shopping cart, and the shopping cart has a mass of 25, and it has a velocity of 4, which means it has a momentum of 100 momentum units, kilograms meters per second. Now that's before. Now it is going to scoop up a shopper, and afterwards, since this so afterwards what I know is that the velocity, instead of being 4, is now 1.17 meters per second, which makes sense. It's going to slow down because it picked them up. I want to know what the shopper's mass is. So the way you saw this is you say the momentum beforehand has to equal the momentum afterwards. So the momentum beforehand is 100 units. That's what it's afterwards. The momentum equals 100. Momentum equals mass times velocity. Let's see what the mass of this system is. The mass of this system can be found by multiplying the net mass times the net velocity, which is 1.17. Now when I divide both sides by 1.17, what I get is, hang on a second, I've got to cheat and look at my my homework assignment because I don't want to get out my calculator. What I find here is that the total mass of the system is, so to say, M total, let's call it, because it's the total of the cart and the shopper, equals 85.47 kilograms. But let's not forget that 25 kilograms is a shopping cart itself, so we're going to subtract 25 from this. And when we do, what we're going to come up with is 60.47 kilograms, or 60.5 kilograms. Alright, let's keep going here. Ooh, I like these. Okay, I got two train cars above are going to be joined together after they collide. How fast will they be going once they're coupled? Okay, so what we have to do here is we say that the total momentum beforehand equals the total momentum afterwards. So what we need to do is figure out what is the total momentum of this system. Now the system is broken into two parts. We've got this part and we've got this part. So what we have to do is figure out what is the momentum of each. So what we find then is the momentum of this one here is going to be 7,000 times, this one right here, is we're going to say 17 times 7,000. Let's see what that equals. And that's going to give me wrong thing. That's going to give me 119,000 units of momentum, which are kilogram meters per second. And now I have to do the same thing here. I would say 13 times 5,000. So if I say 13 times 5,000, I get 65,000. Oops, wrong one. I get 65,000 units of momentum. And since both of these vectors are pointed in the same direction, I'm going to add them together. If they're pointed in opposite directions, I'd subtract. But in this case, I'm going to add these two. And when I add them together, what I get is 184,000 units of momentum. Now that is, well, let's just call it total momentum total. We'll call it MOM total. So the idea is the total momentum of the system beforehand equals the total momentum afterwards. So let's see what we're trying to find. We're trying to find is how fast will they be going when they're joined together. So afterwards they're going to have this much momentum. So I'm going to say 184,000 units of momentum equals the total, that's the total momentum, equals the total mass, which I know to be, let's see, 7,000 plus 5,000, that's 12,000 kilograms, times V total. So I'm going to divide both sides by 12,000. And what I'm going to find then is that the V total for the joined cars is going to be 15 meters per second. And you know you've done it right if this happens. Look, clearly the slow one's going to speed up when it gets hit, so it has to be more than 13. And the fast one's going to slow down, so it's got to be less than 17. And lo and behold, 15 meters per second, I should point out, it is a vector, so it's going that way. It is right in the middle where it should be. Let's try another one. I love these ones. Okay. So again, let's see what I've got here. Now, fortunately, looky here. This one, 17 times 7,000, 17 times 7,000, that helps. I have 119,000 units of momentum going this way. And now, in this direction, the opposite direction, I've got 5,000 times, let's just do this, I should be able to do this in my head, but I can't. 5,000 times 25, that gives me 125,000 units of momentum that way. Now since they're going opposite directions, I have to subtract the two. So when I subtract the two, what I get is I get 6,000 units of momentum, And since this value is larger, 125,000 is larger, then since this is the larger momentum, this is the direction it will be traveling. So what I find then is that the total momentum of the system is going to be in this direction, and it's going to be equal to 6,000. So what I have is a momentum in this direction of 6,000 momentum units. And again, the cars are joined together, so the combined mass, once again, is 12,000 kilograms times the velocity. And so when I divide both sides by 12,000, I think I can just about do this one in my head, I believe, unless I'm very mistaken. What I'm going to come up with is half. So the velocity in this case equals 0.5 meters per second this away. Well, hope you enjoyed as much as I did, kids. Catch you on the next assignment.